Today we will talk about a couple of operations that can be done to vector fields that will help us generalize stuff like Green's theorem to 3 dimensions. The first one we're going to talk about is the curl. So if we have a 3-dimensional vector field, something like f equals pi plus qj plus rk, we define the curl of f as a new vector field, where the components of the curl are differences between derivatives of p, q, and r. Now, you might recognize right away the dq dx minus dp dy in the third component. That's something that we were working with for two-dimensional vector fields. Specifically, it was the integrand that we had in Green's theorem. And that's absolutely not a coincidence. The curl is going to be the tool that generalizes most of those results involving those derivatives to a three-dimensional setting. In fact, if we took a vector field in 2 dimensions, something like f equals pi plus qj, where p and q depend on x and y, we can turn this into a 3-dimensional vector field by attaching a 0k, and while p and q don't depend on z initially, we'll just say that they're functions of x, y, and z, where the z doesn't do anything. Since the r here equals 0, then dr dy and dr dx are both 0. And since p and q are not making depend on z, then dq dz and dp dz are both equal to 0. So the curl of this vector field is just going to be this third component. Oops, I forgot my f. And so in a sense, we've turned our vector field in the xy plane into one that sticks out perpendicularly into three-dimensional space. So the k here is taking this magnitude along a vertical direction, and so the magnitude is the integrand from our Green's theorem. If we want just the magnitude, we could take the dot product of this with k, and that would, because k dot k of course is 1, I mean it is a unit vector, and so we can replace dq dx minus dp dy with this curl dotted with the k vector. In other words, Green's theorem can be written like this. So normally we have the integral, the line integral of p dx. Let me actually write this out. The line integral p dx plus q dy over the boundary curve c is equal to the double integral over the inside d of partial q dx minus dp dy dA. But if this side over here is just the integral of f dot dr, I mean that's what this actually means. And then this side we're now replacing with the curl. And this is essentially going to be the form that we're going to see later on in section 16.8 when we get to what we call Stokes Theorem, where we'll have essentially the same idea, except instead of looking at things in the plane, we'll be looking at things on surfaces. And so this k will relate to the surface, and that will turn into what we call a surface integral. That's actually something we'll get into 16.7. We don't really have the tools to work with that quite yet, but we are building up to that. Now, obviously, the formula for curl is kind of involved and probably a little hard to memorize. We've got all these derivatives going on here, and we want to figure out how we can remember which one's which. But let's take some inspiration from the cross product. So let's say I have two vectors. I'll call them A and B for now. A will have components of A1, A2, A3. B has components of B1, B2, B3. If I write out the cross product of these, it looks like A2, B3 minus A3, B2, I, plus A3, B1. Make that 3 look like a 3 and less like a 1. Minus A1, B3, J, plus a1 b2 minus a2 b1. Okay. These look very similar. Both of these are differences. Each of the components is a difference between two things. And actually, if you pay attention, if you think of B as having components of P, Q, R, and A kind of having components of A1 being the derivative with respect to X, A2 being the derivative with respect to Y, and A3 being the derivative with respect to Z, then we can think of A2B3 as the derivative with respect to Y of, well, I guess I was saying here that B1 is going to be P, B2 is Q, and B3 is R. So this would be derivative with respect to Y of R, which is exactly what we have here. A3, B2 we could view as the derivative with respect to Z of Q, which is exactly what we have here. In fact, everything here lines up exactly the way the cross product works. Everything in the curl and everything in the cross product really do line up very nicely. And so we'll essentially view this as a cross product, even though that's a little bit of abusive notation here. Technically, we can't really make a vector out of derivatives, but we'll consider it a vector just because it'll make it easier to memorize stuff. We call that vector Nabla, or the book is actually referring to this as del. I like to avoid using del because sometimes that's used for other things. We've actually seen this Nabla before. Remember when we took the gradient we use the same notation of Nabla, but we can think of it as taking this vector here, the pseudo vector, you might say, and multiplying it by f. Where multiplying by f multiplies each component by f, and that multiplication really is just taking a derivative. So ddx times f is really the derivative of f with respect to x. Then we have the derivative of f with respect to y, and the derivative of f with respect to z. In terms of the curl, now we're doing essentially the same thing, except now we're treating it as a cross product. And so a lot of times people will just write out curl. Instead of writing curl of f, they'll just write Nabla cross f. And they'll just treat it as this being the actual notation for what the curl is. Now, we can use any way that we take the cross product to do the curl. And specifically, if you use the determinate method, the format of this is pretty nice. Remember, when we take the cross product using the determinate, we make the first row ijk. Second row here is the first of our vectors. In this case, it's not technically a vector, but it's the Nabla that we have. So ddx, ddy, ddz. And then our third row is our second vector. In this case, the f here, it has components of p, q, r. So you can think of the curl as being the determinant of this 3x3 matrix, where the first row are the ij's and k's, second row are our partial derivatives, and our third row is the actual vector that's being put into the curl. Now, we've actually gone from the cross product of abusing notation by mixing vectors and numbers in a matrix to abusing it even harder by mixing those vectors and functions with differential operators. The mathematician in me is like, that we can't do that, but the point here is less of this is specifically actually a determinant of something, and more that this is a lot easier to remember the format of the curl in this way. And this is the way I'm going to approach doing all the problems. So let's go ahead and take the curl of a vector field. So problem 3 here, they actually has two parts to this problem. They want us to find the curl and the divergence. We are not talking about the divergence quite yet. We'll talk about that Maybe in another video. I'm not sure when I'm going to actually cut this one, but we'll come back to this problem after we've defined the divergence, and for now we're just going to do part A. So we're trying to take the curl of f, or you could write this as Nabla cross f if you want to. Remember, that is a determinant. We have I, j, k. We have the derivative with respect to x, y, and z. Now, in general, you probably don't want to write those first. You probably want to write your vector first. That tends to take up more space. This time, it's not too bad. We have x, y, e to the z is our first component. That's our p. We don't have a j component or y component, so we'll go ahead and make that a 0. And then finally, the r, our third component, is yz e to the x. Now, when we take the determinant, we expand along the top row. That means this I gets associated with this 2 by 2 down here. So we'll have a 0 with yz e to the x. We have a derivative with respect to y, and then z. That determinant is going to be multiplied by I. For j, we take out the middle row, or sorry, middle column, and we look at the stuff on the side. So we have a ddx, and a ddz, and an xy e to the z, and a yz e to the x. Let me make that not look like a 2. That's going to be multiplied to j, but this one does have to have a minus sign here. And those of you that know anything about linear algebra or determinants, that will make a little bit more sense to you. Unfortunately, here we don't really have time to go through all the determinant stuff. Then finally, for k, we take out this column, and we're left with this 2 by 2 over here. And I'm running a little bit out of space. That should be okay. Oops. It did not like me clicking on the bar. You have a K in there. Okay, now we go through all these. So for 2 by 2s, we basically do diagonals. So we're doing the derivative with respect to y of yz e to the x. The derivative of that is z e to the x minus the derivative with respect to z of 0. So we have a 0 there. That's our I component. Our j component, we take the derivative with respect to x of yz e to the x. Of course, there, e to the x is the only part that we care about, and its derivative is still e to the x. So we have yz e to the x. Then minus the other one, we have the derivative with respect to z of xy e to the z. Same kind of thing there. And then finally, for our k component, we have the derivative with respect to x of 0, so 0, minus the derivative with respect to y of xy e to the z, which is going to be x e to the z. And if you want, we could actually go ahead and just take out the zeros. You could use the minus sign here to swap the order of these. Really, there's not too much simplification, just kind of maybe cleaning a few things up. Instead of writing that out, let's go ahead and move on to another example. Here, problem 6, the same directions here, so this was problems 1 through 8. Again, we're going to ignore the divergence part of this for now, and come back to it later. But we're looking at the curl of this vector field. So this one, I definitely want to write my third row first, because these are a little bit longer to write out. So you have a natural logarithm of 2y plus 3z. We have a natural logarithm of x plus 3z. And we have a natural logarithm of x plus 2y. And then over these, we have I, j, k, derivative with respect to x, derivative with respect to y, derivative with respect to z. I'm not going to have room to write them out the same way I did there, at least not on the same line anyways. So start with I, we have this 2 by 2 here, so you have natural logarithm of x plus 3y, 3z, natural logarithm of x plus 2y. We have the derivative with respect to x, with respect to y, derivative with respect to z. That's our I component. Then we have, for j, we take off the middle ones and just look at the two sides. We have natural logarithm of 2y plus 3z, natural logarithm of x plus 2y. Here we have derivative with respect to x, derivative with respect to z. That's j. I still didn't have enough room, did I? Finally, k, we have just this 2 by 2 here. We have 2y plus 3z, and then natural logarithm of x plus 3z. It's going to be d dx and d dy. Alright, now we actually get to take our derivatives. We take the derivative with respect to y of the natural logarithm x plus 2y. Remember, natural logarithm, we end up with the derivative of the function on top, and the inside of the function, or should say the derivative of the inside on top, and the original inside on the bottom. So we have an x plus 2y down here. The derivative of x plus 2y with respect to y is going to be 2. Then we take the derivative with respect to z of the natural logarithm of x plus 3z. Same kind of thing there. We have the x plus 3z on the bottom, and the 3, because we're differentiating with respect to z. That's our I component. And there's not really any simplification we can do there, other than maybe combining the fractions, and I'm not convinced that would actually really simplify it that much. Moving on to j, we have the derivative of natural logarithm of x plus 2y with respect to x. The derivative of the inside here is just going to be a 1 this time. Derivative of z with respect to z of ln of 2y plus 3z. Derivative of the inside is a 3. So you have 2y plus 3z on the bottom and a 3 on top. Finally, derivative with respect to x of natural logarithm of x plus 3z. We'll have an x plus 3z on the bottom, and we end up with a 1 on top. And finally, derivative with respect to y of natural logarithm of 2y plus 3z. We end up with 2y plus 3z on the bottom. We end up with a 2 on top. And again, none of this really simplifies very nicely. Maybe you can combine fractions if you want to, but all the denominators are separate. I mean, I guess technically here, this one and this one are not separate, but those are in different components. I mean, in a particular component, the two denominators are always going to be separate here. But that's how you take the curl. It's maybe a fairly lengthy process, just because taking the cross product was already a lengthy process, but it's fairly straightforward. Now, what can we actually do with the curl? Well, one of the first results about the curl is pretty easy to show. If we have a function of 3 variables where the second derivative, it has second derivatives that are all continuous, then the curl of the gradient of that function is always equal to the 0 vector. So this is very similar to one of our results from before, which we'll explain after we prove this. And it's actually pretty easy to prove. So we just have to go through the whole process of actually taking the curl of this. So remember, the gradient of f, so Nabla f, is equal to the derivative with respect to x of f, I, derivative with respect to y, j, and derivative with respect to z, k. We take the curl of that. Now, you can go ahead and do all the stuff with the determinant and everything like that. I'm going to kind of skip right to what we get from that. We end up Well, let me skip the very first step at least. Um, when we write this out, we end up with the 2 by 2 determinants of the derivative with respect to y and z of df dy df dz. That's our I component. Our j component is the derivative with respect to x, derivative with respect to z, then the derivative of f with respect to x, derivative of f with respect to z. And same thing with the k component, we have derivative with respect to x, derivative with respect to y, then the derivative of f with respect to x, and derivative f with respect to y. So when we go ahead and go along the diagonals, we have the derivative of f with respect to z, but then with respect to y. So that's going to be our second derivative of f, first with respect to z, and then with respect to y. Then we have another second derivative. So the second derivative of f with respect to, this time is with respect to y and then z. That's going to be our I component. Same kind of thing here. We have the second derivative of f with respect to z and then x, minus the second derivative of f with respect to x and then z. And finally, we have the second derivative of f with respect to y and then x, minus the second derivative of f with respect to x and then y. But since we are assuming that the second derivatives are continuous, we have Claros theorem. That says that changing the order of integration, changing the order of differentiation doesn't change the result as long as we have continuous second partial derivatives. And so under that assumption here, this term here and this term here are the same thing, but we're subtracting them, so they cancel each other out. We get 0 for the I component. Same thing here. We swap dx and dz, we get the same result, we're subtracting them, so we get 0. And finally, same exact same thing here, everything turns out to be 0. We have 0i, 0j, 0k, or the 0 vector. What this actually means, remember that a conservative vector field is one that is the gradient of some potential function. If f is conservative, then its curl has to be 0. Automatically, just because f equals Nabla f for some little f, and then the curl of that has to be 0. Now, of course, here, I guess we're assuming here that the components of f do have continuous derivatives. So the derivative of each component of f with respect to each of the variables has to always be continuous, so that the second derivatives are continuous. But that's usually a pretty simple condition, and usually it's going to be true. Now, this is essentially the equivalent of our condition that the derivative with respect to q with the derivative of q with respect to x equals the derivative of p with respect to y. For a two-dimensional vector field, this was the condition that we had that was implied by it being conservative. And this was the condition that needed to be true in order for it to actually be conservative. Well, here we're essentially saying the exact same thing, but we have three different components that we're working with. This component, this equality is just saying that the k component of our curl is equal to 0. For a two-dimensional vector field, that's the only component that wasn't 0 automatically. Of course, the opposite is not always true. Just because the curl of f equals 0 does not imply that f is automatically conservative. But it's almost always true. As long as the domain of f is nice, it's going to work out. And the book mentions this for a vector field that's defined on all of three-dimensional space. So here, as long as f is defined on all three-dimensional space and the curl of f is 0, and of course the components have to have continuous partial derivatives, then f is a conservative vector field. This is actually true in a slightly more general sense as long as our domain is what we call simply connected, just like we had for 2 dimensions. The only issue here is that talking about simple connectivity is a little bit harder to define outside of the plane. For instance, we saw that if our domain was missing just the origin in 2 dimensions, that caused a problem and forced us to not be able to have a conservative vector field there. At least the vector field that we took a look at in that section. But in 3 dimensions, that's actually not true. If a vector field has curl 0 and is defined on everything except for the origin, it actually still is conservative automatically, because just missing the origin is not enough to make it not simply connected. There, maybe if it was missing an entire line or something like that, then we could actually say it. But the point here is we're not really going to get into exactly what that condition means. Mostly we'll just be looking at things that are going to be defined everywhere. So let's put this to work. We have a vector field here. We want to know, is it a conservative vector field? Is there a potential function, little f, where this capital F is equal to the gradient of it? Here, we're just going to take the gradient first. This is basically, we're just testing whether or not our derivatives turn out equal to each other, like we did in the last section. When we take the curl, we'll go ahead and put our 3 components as our third line. Then above those we have I, j, k, and derivative with respect to x, derivative with respect to y, derivative with respect to z. And I'm not going to explain every step of this every time, so let's go ahead and just expand along the top row. That's our I component. Our j component. And we have our k component. We go ahead and go along the diagonal, so the derivative of this with respect to y is going to be 4x squared z cubed. Derivative of this with respect to z is going to, we got to bring down that 4, so 4x squared z cubed. That's our I component. Here we take the derivative with respect to x of this, so we end up with an 8xyz cubed minus the z derivative of this, so we end up bringing down that 4 again. We have 4xyz cubed. Now, one thing you could note right away, so the first component here, we can see already that they cancel out. We can actually say that this is 0 times I. This one, actually, we already can see that they don't. These are not the same thing. They're pretty similar. They are like terms, but their coefficients do not cancel. We end up getting a 4 overall, or a negative 4 with that negative that's outside there. So negative 4 xyz cubed j. We could actually stop there because we can already see that this is not going to be the 0 vector. So the components do not ever combine with each other. The fact that this is not 0, it doesn't really matter what the k is, because that's going to force the result of this to not always equal to 0. Let's go ahead and finish it up, though. We'll go ahead and take the derivative of this with respect to x. So we have a 2xz to the 4th minus the derivative of this with respect to y. That means we have an xz to the 4th. Turns out that doesn't go to 0 either. They are like terms again, which is nice. But we end up getting an xz to the 4th k. So this is not 0 in general. That means this is not a conservative vector field. There's no point in trying to find a little f because we can see right now there just isn't one. It actually turns out that this one isn't too far off from being conservative. The very fact is that if this had an additional 2 in here, then these would actually cancel out. We'd have an 8 here instead of a 4. And if we had an additional 2 here, this would be a 2, and these would cancel each other out. Well, those are exactly the same thing. Those were the original p from f. So if this was actually 2x, y, z to the 4th, these would actually cancel out. That component doesn't even have any effect on the I component of the curl. So they gave us one that was not very far off from one that would be conservative, but this one just isn't. What about this vector field? So problem 16, we have I plus sine zj plus y cosine zk. We want to know, is this a conservative vector field? And if so, can we find a potential function for it? So we'll just start with the curl. The curl of f. Again, I'm going to put my vector in first. My vector field in first is my third line. So I have 1 sine z and y cosine z. Above those we have I, j, k. Derivative with respect to x. Derivative with respect to y. Derivative with respect to z. That turns into, we have sine z, y cosine z, cosine z, with respect to y, with respect to z, minus, then we have, we have 1 and y cosine z, and finally we have 1 and sine of z. We go ahead and take those derivatives. Derivative with y cosine z with respect to y is just cosine z. Derivative with respect to z of sine z is cosine z, but we have to subtract it. So those actually will cancel each other out. That's very nice. Here, the derivative with respect to x of this, well, there's no x's involved, so that's just 0. And then we're differentiating 1, so that's also 0. I wonder if those cancel out. Yeah, we only have zeros there. Same kind of thing actually happens here. There's no x's here, so we end up just getting 0, and of course we're differentiating 1 again. So in fact, the only one that didn't have zeros just automatically was the I component, and there they actually did cancel out. We do get the 0 vector here. That means that this vector field could be conservative. It doesn't mean, really the fact that curl equals 0 just implies that it could be. It doesn't imply that it necessarily is. But we do know here that f is defined everywhere. There's no x, y, or z that can't be plugged in here and get a result. And if we take the derivatives of these, we just have nice continuous functions. Well, with 0, we have zeros or cosine of z. Here we'd have either 0 cosine z or negative y sine z, if we look at all the partial derivatives. All those are nice continuous functions. We don't have any issue with those. So that means that this vector field is definitely conservative. But that doesn't tell us what the potential function is. We want a little f where capital F is the gradient of that, which essentially means we want the x derivative of f to equal the x component of f. We want that to equal 1. With respect to y, we want it to equal sine of z. And if we differentiate with respect to z, we want it to equal y cosine z. We now know that there is a solution to this. There is an f that makes this true. We just need to find what it is. I'm going to go ahead and take my formula with df/dz and integrate it with respect to f. I'm picking that one because it's the most complicated one that I can easily integrate. All these would actually be pretty easy to integrate in this particular case. Sometimes things can be a little bit more complicated than you want to deal with, but this one's not too bad. So I'm going to take this one and I'm going to integrate it. So I'm going to get f of x, y, z. The integral of y cosine z with respect to z, and keep in mind, the y is not affected here. Cosine of z, when we integrate it, we get sine of z. Now, of course, this is plus a constant. But that constant might depend on x or y. I'm going to write this as a function g of x and y. I need to find out what that is. And probably the easiest way to tackle that is just differentiate this particular thing we have here. With respect to x of this thing, well, the y sine z is 0. We get the x derivative of g. And we need that because these need to be the same thing. It needs to equal 1. We can do the same thing with y. Derivative with respect to y. So the derivative of this is just sine of z plus the y derivative of g. That needs to equal the df/dy that we have up here, which is sine of z. So we can see right here that gy is 0. That means that g actually does not depend on y. But it does depend on x. G sub x is equal to 1. So we'd want to take g sub x equals 1, and we'd want to integrate it to get what g is in terms of x. Well, the integral of 1 is just x, or technically x plus a constant. So g of xy is equal to x plus a constant. Again, I'm just assuming here that it doesn't have any dependence on y, so integrating g sub y equals 0 just gives us that constant plus some function of x. The point here is I can ignore y just because I already know its derivative with respect to y is 0. But I can now put that function into here and get that my potential function looks like y sine z plus x plus some constant. And of course, any constant works there. If you're looking for just a single one, you might leave out the c. Just y sine z plus x is our potential function. Alright, so I'm going to leave this here. This is all our stuff about the curl. In our next video, we're going to talk about another operator called the divergence. So meet me there and we'll learn all about that one.